It's Chinese poem, it looks like. Anyone has seen this already? If you have seen this already during this weekend, could you please raise your hand? Okay, excellent. Look at it. Check whether what is so special about this one. It's quite beautiful. Yes? Okay, anyone who have not seen this before but can guess what it is about, could you please raise your hand? Excellent. So what is that about? So there is an English one. This is by an English scientist called James Jeans. Okay, so James Jeans says how I want to drink alcoholic, of course. So why he wants to drink? Because it is after the heavy lectures involving quantum mechanics. Okay, so this part is by James Jeans. So there are relationship between these two, and then somehow people continue his writing. All of the geometry air Planck. So this is the scientist Max Planck who has developed quantum mechanics. Okay, is fairly hard. And if the lectures, let me write it here, were boring or tiring. So if the lecture about this quantum mechanics is quite boring or tiring, then any odd thinking. So what is meant by odd here in this? Odd thinking, any odd thinking. It's not even thinking, odd or even. This odd means weird. Okay, very good. Strange. Any strange or any weird thinking was on quartic equation again. Okay. Okay, so by this time, let me ask again. So these two are related. If you know this one, of course, you will quickly understand what is this about. Let me know. If you understand what these two are about, could you please raise your hand? Okay, if you are still very confused what I'm writing, could you please raise your hand? Okay, good. If you are confused, read it in Read it. So how do you read it? Oh, how? Okay, what you have just read? 3.141559. What's that? Pi. Okay, so this is pi. So this is the, so we call this mnemonic. So this is to help our memory. So this is 3.14159. And then this one is 2, 6, 5, 3, 5. Okay. 8, 9, 7, 9, 3. Okay. This is 2. This is 2. 3, 8, 6, 4, 6. Okay. Now if you look at it, so what is so special? This is also about pi. So what is it about pi? How I want to drink. How I want to drink. 3, 1, 4, 1, 5. So this is 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is okay. This is very, very long. This one is. So this is 2, 6, 5, 3, 5. It looks correct, right? This is at 8, right? So this is 8. 9, it should be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. Here, 7. Here, 3, 4, 5, 9, 3. 3, 8, 4. Yes, 4. 6. Okay. So this one is a German word, means Mr. Okay, Mr. Plant. So 4, 6. And then this is 2, 6, 4. Not very good. 3, 2, 3, 8. Right? 8. And then you have still 4, and then 6, and then 2, 6, right? And then 4, 3, 3, 1, 2, 3, 4, 5, 6, 7, 8. 3, 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 5. Okay. So if you remember this, you can. Now this one, both of them. This one is very beautiful. Actually, this one I've read it over the weekend from some Facebook or Dcard. And then, and then I checked the web page, and then a long time ago there was already a very similar poem like this. It's not one temple; it's like one big stone. They use a different word, and then this one they use another word. Like there are 2 monks, okay, and then they use this one. So there are some different variations of this one, but then afterwards it becomes quite different from this one. So I think this is also very beautiful. And from this one, this first part, from what I checked from the Wikipedia, it is by a scientist, James Jeans, but probably the latter part is not written by him, and then someone complete and make more digits of this part. Okay, yeah, I hope you like this. Okay, so next. So what is a Black Friday? Everyone knows a Black Friday, right? So a Black Friday is a Friday that happens to be the 13th. Okay. So next month we will have a Black Friday. Okay. So November the 13th we will have a Black Friday, and then yes. And I want to show every year, no matter which year, there must be at least some Black Friday, at least one. So how can we show? So there could be many different years, right? So I can show to this year, next year, and so on and so forth. But it seems that how can I show every year? Or of course we can show it by certain kind of contradiction. But it doesn't look like if a year doesn't have a Black Friday, there is something wrong. Okay? So what is the best way to show this? Okay? So we have a strategy called proof by cases. Or we prove it by cases. this strategy is very useful. We want to show that every year there is a Black Friday. We may be showing that, okay, this kind of year there is a Black Friday. And then next kind of year there is a Black Friday. Or then a third kind of year there is a Black Friday. And so long as we can what? We can check every possible types of year there is a Black Friday, and we can show that every year has a Black Friday. Am I correct? So it is like it's like what? It's like, so for instance, so let's do something easy, okay? So let's take a look of a number integer n. We want to show that the square of this n is either a multiple of, okay, we want to show that the square of this n cannot end with the digit 7. Okay? So for instance, 1 square is 1, 2 square is 4, right? 17 square is something like 289, so it ends with 9. We want to show that for every n square, the last digit is not equal to 7. So how can we show? So naturally, we are going to show that, okay, 0 square does not end with 7. 1 square does not end with 7. 2 square does not end with 7. Up to 9 square does not end with 7. Now, if we have shown all these cases, then we know that whenever a number looks like 10 times something like a k plus a certain digit L, okay, so let's say L, we want to look at this square, and then we know that this L is between 0 to 9, then it cannot end with 7. Do you understand my point? Okay, so every number, you can write it down as 10 times something plus the last digit. So L is the last digit. Is that okay? So for instance, if you have 1, 2, 3, then it is equal to 12 times 10 plus 3. Is that okay? Now the square of this one always depends only on this part. It does not depend on this part. Does that make sense? Yeah, because the square of this one, let us expand it. The square of this one is equal to what? It's equal to 100 times k square plus 20 times k times L plus L square. Is that okay? So it is like you have a k square, the number k square, but you add 2 zeros after it. You have a number 2 times kl, but you add a 0 after it. Is that okay? And finally, you have L square. So if you add things up together, only this L square can affect the last digit. Is that okay? So if you are okay with this, then that means that to check n square whether the last digit is equal to 7 or not, we just need to check all these 10 different cases. And then we show that 0 square is equal to 0, so it is not 7. 1 square, 1. 2 square, 4. 3 square, 9. 4 square, 6. 5 square, 5. 6 square, 6. 7 square, 9. 8 square, 1. 8 square, 4. 9 square, 1. And that's it. So all of these cases does not end with 7. So this does not end with 7. Okay? Now we are actually using this kind of thing. This technique is called proof by cases. Proof by cases has a very good benefit. We are looking at a specific case, one at a time. And then because we are looking at a very specific case, there are properties that we can use normally. And then we use the property and then show that it is not equal to this. Okay? So if I summarize what we have done just now, so we are showing that what? So we are listing out their different cases. So we are showing that case 0. Okay, when the last digit is 0, then it does not end with 7. It is not ending with 7. For case 1, it is not ending with 7. Up to, we are showing case 9, we are not ending with 7. Okay, we are showing this. And then once we have shown this, we are concluding what? We are concluding, so this is what we have shown. We have shown just now. So this is the conclusion. So the conclusion is all cases, any cases, it does not end with 7. Is that okay? This is what we are showing. So it's quite strange. Okay, we are showing this one is this one and this one and this one and this one. We are showing and. And this one is all cases. All cases means that no matter we are in case 0 or in case 1 or in case 2 or in case 9, then we don't get this. So we are using what? Using symbols. Okay. What we have just shown is that, let's say we have P1 implies Q, we have P2 implies Q, and then we have case statement PK implies Q. Then we are showing that using this, we are showing that P1 or P2 or PK implies Q. Okay? So we are showing that this one is correct, and this one is correct, and all these things are correct, and also the last one is also correct. Then we have this one. So can you see this? So this side is about and. This side is about or. So why is it like this? So this part is and, right? In fact, these two things are equivalent. They're equivalent. Okay, so why? So let's briefly look at what is meant by A or B. Okay, so if I have some statement P or Q, this is difficult to understand, right? If you change it into using this and or not, so what is P implies Q? Okay, very good. Not or Q. Okay, so this is equivalent to not P or Q. Is that all right? Is that okay? Okay. Now let's take a look of this right-hand side. So this right-hand side is more complicated. It's P1 or P2 or ... up to PK. This one implies Q, right? So this will be what? This will be not the first part. Not the first part, and then what? Or Q. Am I correct? Okay. So what is meant by not the first part? Then we use De Morgan's law. Okay. Okay. We use De Morgan. Yeah. Okay. We use De Morgan's law, so we will have what? Not of this one is equal to what? Not of this one is. You just not everyone, but and becomes or becomes and. So it becomes not P1 and not P2 and ... and. This one is not PK or Q. Right? Right? And then think of this and like a plus, think of this or like a multiply at this moment. So we can use the distributive law. Okay, so it's like 1 plus 2 times 3 is 1 times 3 plus 2 times 3. Okay, so this one is equivalent to, so we have the first one, not P1 or Q, and then and, not P2 or Q, and ... and, not PK or Q. Is that okay? And then now once we have this one, this is P1 implies Q, this is P2 implies Q, and the last one is PK implies Q. So this is equivalent to this one, equivalent to this side. So we are done. Okay? So this is the reason why we can use this kind of logic. Okay, if you want to show something implies something, then we can make the first part into cases, and then we show that each of the case will imply the same thing. So we get this. Okay. Okay, so let's do one more example before we go back to the Black Friday example.